Then I will show one of the energy-efficient superconducting logic families, which we call AQP. I will show some very basic operating principle and some digital systems we have recently developed using this AQP technology. And finally, I will show some qubit interface circuits using AQP. One is the microwave pulse generator, and the other is the flexible circuit. Okay. So recently, the power demand for IC systems has been increasing very dramatically because of the advent of new technologies such as AI and IoT. And so these technologies require a handle of a huge amount of data. So recently, in the worldwide, this kind of very large-scale data centers are being built. And as a result, now approximately 10% of the total electricity power is now used for this kind of ICT systems, and is estimated to reach 20% in a decade. So for future ICT, we need a very low-power digital circuit technology to achieve even much more energy-efficient ICT computing systems. And as you know, the modern computing systems is composed of semiconductor transistors. And what is great about transistors is that people have continuously miniaturized the device size, and thanks to this, so this is called Moore's law, meaning that the number of transistors on a single computation using your computers. And Moore's law is also important from the viewpoint of energy efficiency for computing. So this shows the average energy dissipation per switching or per transistor versus transistor size. And this shows that the average switching energy dissipation decreases with decreasing the transistor size. This is because the charging energy for each transistor decreases with device miniaturization. But this kind of device miniaturization has some physical limitations. So maybe around here it will be impossible to improve the energy efficiency. Maybe somewhere around here. So now it's time to think about alternative way to improve the energy efficiency for computing. And one promising approach is to replace semiconductor transistors with some other devices such as superconductor devices. And superconductors has very good physical features for digital applications. For example, it does not have resistance. So if we make interconnection using superconductors, we can easily achieve interconnection without dissipation. And secondly, it's the magnetic flux quantum, meaning that the magnetic flux threading a superconductor loop is quantized. So if we encode the data using the trapped fluxes or flux quanta in a superconductor loop, we can store data without energy dissipation. And lastly is the Josephson junction. So Josephson junction is a thin insulator sandwiched by two superconducting electrodes. And this junction normally behaves like a superconductor, but once you apply a small amount of current, this junction switches and it behaves like a normal conductor. And using this switching behavior, we can perform logic operation with very small energy dissipation. So these show that in principle, we can perform fundamental information processing in an energy efficient way using superconductors. So people have investigated superconductor logic families for a long time. So this shows a very brief history of superconductor logic. The first logic was called cryotron, invented in 1956. So in this logic, the data was encoded by the state of some superconductor cylinder. But this cryotron was not practical because it was quite slow because of very large inductances. And the second generation was the voltage state logic, where the Josephson junction, this cross symbol, were introduced. And in this logic, the data was encoded by the voltages across the Josephson junctions. And so this was low power compared to this one, but still dissipates some large amount of energy. This is because the Josephson junction need to generate voltages to represent data. So the third generation was invented, which is single flux quantum or SFQ logic, in which the flux quantum encoding was introduced, meaning that data was encoded by flux counter in this kind of superconductor loops. Okay, so in this logic, that data can be stored without energy dissipation. So the history shows that we have improved the energy efficiency of superconductor logic families, by adding more physical features of superconductors. And recently, in the last decade, even more energy efficient SFQ-based logic families have been proposed. So the point is that in this SFQ logic, it has some resistors to provide bias currents to the Josephson junctions, and these resistors dissipate some static power. So in some new logic, this kind of resistors were completely removed to achieve zero static power, and also in some logic, dynamic power dissipation was also reduced by introducing adiabatic switching, which I will explain later. And today I am going to talk about one of the energy efficient SFQ-based logic families. It's AQFP. So AQFP stands for adiabatic quantum-flux-parametron. So originally the quantum-flux-parametron, or QFP, was invented by Professor Goto in 80s. And recently, we revived this technology as an energy-efficient logic family by optimizing the circuit parameters plus establishing the design methodology for this technology. And okay, so this shows the fundamental gate in AQFP logic. So I will quickly explain how this works. So initially, these two Josephson junctions behave like current sources with opposite polarities. So the currents from these sources cancel out each other. Okay. So no signals appears at the output port. But if you apply excitation current to this port, one of the Josephson junctions switches depending on the input signal. So here we assume that J1 switches, and in this case the polarity of J1 is inverted like this. So now the currents from these two sources are added together, and now we can see some output currents at this port. And in AQFP, the logic state is represented by the polarity of this output currents like this. Okay, so this circuit can operate with very small energy dissipation because of zero static power and also plus adiabatic switching. And it also has some features like high sensitivity and low current drive, and these features are also very important in some applications. So next I will explain why AQFP is so energy efficient compared to conventional logic families such as CMOS. So first, let's think about what limits the energy of conventional logic families such as CMOS and SFQ. And the energy state of a logic gate is normally represented by this kind of double well potential energy, and where each well represents a logic 0 or 1. And here, if you want to switch this device, you need to perform work on this device. And as a result, the potential is tilted like this, and the circuit state switches to the other side very suddenly. And apparently, this process is not reversible, so the work performed by power supply is totally dissipated, meaning that the energy equal to this energy barrier height is always dissipated for every switching event. But AQFP operates in a very different way. So first, its potential energy shape is reset to a single well like this. And then the potential energy shape gradually changes from a single well to a double well like this. And as a result, the circuit state can switch to the correct side without jumping over this energy barrier. So as a result, this circuit can switch its state with energy dissipation much smaller than this energy barrier height. And furthermore, this process is reversible. So this circuit can switch its state without energy dissipation in the closest static limit. So this is why AQFP is more energy efficient compared to other logic families. And we call this energy efficient switching scheme adiabatic switching. So in adiabatic switching, energy dissipation becomes zero at the infinitely slow speed or the closest static limit. But AQFP dissipates some amount of energy at the finite operating speed. So, the energy dissipation is given by how slowly you operate a circuit, which is quantified by the ratio between the two time constants. So one is the characteristics time of the Josephson junctions, and the other is the duration time or switching event. And this shows the simulated energy dissipation. Okay, so the x-axis shows the rise and fall time of excitation currents. It's a duration time over switching events. So as you go this way, you operate the circuit more slowly. And the y-axis shows the energy dissipation per switching event. And you can see three color lines, and these lines represent results for different circuit parameter sets. And this figure shows that by optimizing the circuit parameters plus operating the circuit more slowly, the energy dissipation decreases very much like this. And very importantly, the switching energy can fall even below this thermal energy kBT, which is not possible from conventional logic such as CMOS and SFQ. And here we clarify the energy benefit of AQP by comparing its energy with some other logic families. So this shows the energy versus delay for basic logic gates such as inverters and buffers, and several logic families like CMOS and SFQ, and this is the result for AQP. And the figure shows that this AQP technology can operate with energy dissipation orders of smaller than that of other circuit technology. So we believe that AQP is...
There's a question, sir.
Okay.
What clock speed you're comparing?
In this figure, 5 gigahertz. 5 gigahertz, yes.
Oh, 5 gigahertz.
5 gigahertz in this comparison.
Is this experimental data, your QFP data points, or is that simulation?
Oh, they actually, we evaluated energy dissipation by both numerical simulation and experiments. Yeah, and for this specific value, I think it's based on numerical simulation. Yeah. So now we believe that our technology is very good building block for future energy efficient computing systems, and also because of very small dissipation, the AQP circuits can operate even inside a dilation refrigerator where the cooling power is very limited, like it's only 10 microwatt at 10 millikelvin stage. So we believe that our circuits can be used as interface circuits for qubits and superconducting photon sensors in the refrigerators. Okay, so far I have focused on the energy of AQP circuits, but we also developed the design methodology for AQP logic to build complex, large-scale digital circuits. And so one is so for example, we established a minimal logic gate design. This means that we can design any logic circuits by arraying some very basic building blocks like this, so like Lego blocks. So this design scheme is very time efficient. And also we developed clocking schemes dedicated to AQP circuits. This is because AQP circuits operate with AC excitation currents, which is very different from DC-based CMOS logic. So we developed some special clocking schemes. And using these design methodologies, we have designed and demonstrated several digital systems using AQP logic. So for example, we developed a 4-bit the prototype microprocessor. We believe that this is a milestone for AQP-based ultra-low power VLSI. And also we developed alternative computing systems such as a reversible computer and neuromorphic hardware. This is because AQP has interesting physical features such as it's very easy. We can very easily introduce stochastic operations. So now we are trying to make neuromorphic device hardware using such stochastic behaviors. And also we developed the single photon image sensors by combining superconducting photon sensors plus AQP circuits, because AQP can be used as a very good AD converters. And so we developed several digital systems, and now we are trying to make some very good circuits, qubit interface circuits using our circuit technology. So first I will show the microprocess generator. Okay, so as you know, both circuit-based and annealing quantum processors have been built worldwide. But to use these quantum processors in real applications, much more qubits need to be integrated on each chip. And to realize such large-scale superconducting quantum processors, one of the most important technologies is the qubit controlling schemes. So currently, the superconducting qubits inside a refrigerator are controlled by the room temperature electronics like this. So there are many coaxial cables between the 10 millikelvin and the room temperature stages. And apparently this is not scalable and deteriorates the scalability of the entire systems. So at some point, maybe we will need to adopt a qubit interface circuit like this, which can control many qubits inside a refrigerator with a few control lines. And now we are developing two types of qubit interface circuits, micropulse generator and flexible circuit. So micropulse generator generates microwave signals for quantum gate operations. And the other is the flux-bias circuit, which generates the DC flux bias for characteristics, for calculating the characteristics of component devices such as qubits and couplers. Okay, so first I will show the microwave pulse generator. So this shows the conceptual diagram of our qubit controllers using AQP, which we term AQP multiplex qubit controller or AQP max QC. So the point is that in this system, the AQP circuits and the microwave techniques are combined to achieve very high scalability. So first, it can generate this kind of microwave signals for qubit control with very small energy dissipation. It's approximately 80 picowatt per qubit, thanks to the very low power operation of AQP. And also, this circuit can be driven by a single coaxial cable because of microwave multiplexing. These features are very important to ensure a high scalability. Okay, so the main part of the AQP max QC is the AQP mixer circuit. So the mixer comprises two AQPs, A and B, which are coupled to this output line together. And we apply the local oscillator current ILO and baseband current IBB, and both of which are coupled to these two AQPs like this. And we also apply the digital input signals IN plus I fix to control the polarity of the output of each AQP. Okay? And this shows the simulation results at 5 GHz. And here we applied 5 GHz LO and a triangular baseband current. And so when these two digital signals have different logical values like this, and in this case, the output fluxes from these two AQPs cancel out each other. So in this case, you see no signal at output port like this. But if they have the same logical values like this, in this case, the output fluxes from the two AQPs are added together at this load line and appears as a microwave signal like this. Okay? So the point is that by using this circuit, we can switch on and off the microwave signal in a very digital way like this. And also this circuit can generate microwave pulse signal like this by mixing the LO and the baseband signals by using the nonlinearity of AQPs. And for qubit control systems, this kind of microwave switching and microwave modulations are very, very important. Okay, and this shows the details of the entire diagram of our qubit controlling circuits, AQP max QC. So the point is that this circuit includes an array of AQP mixers like this, and also a superconductor resonator array like this. And here we apply multitone microwave signals as a LO signal to this drive line. Okay, and we assume that the frequencies of the microwave tones are equal to the resonance frequencies of the superconductor resonators. Okay. So again, so these microphotons are equal to the resonance frequencies of these these microphotons are equal to these resonance frequencies, okay? And as a result, each mixer can generate this kind of microwave pulse signal by mixing the local oscillator signal in the resonator plus the baseband signal, which is which is shared by all mixers, okay? And as a result, these mixer circuits can generate multiple microwave signals for controlling many qubits from a single microwave input. In other words, the cable count for operating this circuit does not increase with the qubit count because of this microwave multiplexing. And we believe this is very important to achieve very high scalable qubit controlling schemes. Okay, and this is the simulation results when we apply the 4.5 GHz and 5 GHz microphotons at this local oscillator input. And this shows the LO signals in each resonators, okay? And we apply a triangular baseband signal as an example. And these are digital currents to control the output of these two mixers, okay? And this is the output at mixer 1, and this is the output at mixer 2. So this mixer 1 generates 4.5 GHz pulses, whereas this mixer 2 generates 5 GHz microwave pulse signals, okay? And the thing is, this shows that each output can be controlled by these digital signals individually. So meaning that we can apply these microwave signals to arbitrary qubits in accordance with a given quantum algorithm. So this is very important. And meaning that this circuit can perform parallel qubit control, okay? And this is very important, and this is not possible in some multiplexing techniques such as time division multiplexing. And we also evaluated the output power and power dissipation for this circuit. And the microwave output power is about minus 76 to 0.6 dBm, and the power dissipation is approximately 80 picowatt per qubit. This is very small compared to other qubit controller circuits. Okay, and we also evaluated the number of multiplexing. So assuming the use of resonators with a quality factor of 10,000, so approximately 2,000 microphotons can be multiplexed on a single line per 1 gigahertz bandwidth. Okay, and this is much more frequency efficient compared to normal frequency division multiplexing used in cryo-CMOS technology. This is because we multiplex continuous microwaves in this drive line, whereas the microwave pulses are multiplexed in normal FDM. Okay, so it is also important to be able to individually control the output power of the circuits. This is because the power for performing quantum gates is different between chips and devices. So it's very important to be able to individually control the power of each output port. Okay, so between these two simulations, so where we again multiplex the two microphotons, 4.5 gigahertz and 5 gigahertz. But thing is that in the right figures, only the power for the 5 gigahertz tone is reduced by 3 dB compared to the left case, whereas the power for the 4.5 gigahertz is the same between the two cases. And now you can see that in this case, only the output power at 5 gigahertz is reduced like this, whereas the power for the 4.5 gigahertz pulse is the same between the two cases. So this shows that we can control the power of each output port by adjusting the microwave tone levels. Okay, so as a proof of concept, we fabricated an AKF Max QC chip and demonstrated the chip at 4 Kelvin. Okay, so this is the micrograph where two AKF mixers are multiplexed by two resonators. They have the resonance frequencies of F1 and F2, and we apply local oscillator current, including two microwave tones, which correspond to the F1, F2 to this line. And we also applied baseband signal and the digital input signals. Digital input signals were applied to control the switching of each output port. And we observed the basic microwave controlling. We did a very basic microwave controlling experiments. So first we demonstrated microwave switching using this chip. Okay, these show the output power of, each output power this is output power for the mixer 1, and this is the output power for mixer 2. And you can see 4 colors, and the colors represent what kind of digital signals we apply. Okay, so the point is that in the left figure shows that the output of mixer 1 is individually controlled by the digital signal I in 1, whereas the output of mixer 2 is individually controlled by the other digital signals I in 2. So each output can be individually controlled. Okay, so this is very important switching operation. And the measured output power was minus 82 dBm, and off ratios were 40 dB. Yeah. This is comparable with other cryogenic microwave switching circuits. And we also demonstrated individual power calculation. So this shows the, each output power versus aftertone in the LO drive signal. So this shows that only the power of the mixer 2 can be individually controlled by changing the aftertone in the drive signal, whereas the power of the output power of the mixer 1 does not change even if we change the aftertone. Okay, so the individual power calculation is also possible. And finally, we did some very basic modulation operation. So where we applied 1 megahertz square pulses to the baseband signal line, and this shows the LO and sideband frequencies. And these results show that baseband signals, 1 megahertz signals, is up-converted by the AQP mixer circuit. Okay, so the switching and also mixing both are passable using our circuits. And finally, we want to compare the specification of various qubit controller circuits very briefly. And this is the result for our circuit, AQP-based circuit. And these are result for cryo-CMOS-based qubit controllers. And these are for the SFQ-based qubit controllers. And the thing is that by using AQP circuits, the power dissipation for per qubit can be reduced very much. It's only approximately 80 picowatt. Okay, and also the number of cable count is very small because thanks to the microwave multiplexing. Okay, so we believe that our qubit control circuit is very good candidate for scalable superconducting quantum processor systems. Okay, but of course it still has many challenges. So for example, we tested this circuit only at 4 Kelvin. So the next step is to test our circuit at 10 millikelvin with superconducting qubits. Okay, and also currently this circuit can generate the microwave pulse signals for X gate operations, but it cannot perform Z gates in the current design. So the circuit needs some design modification improvement. And also, so finally, we need some digital processing circuits integrated with this kind of qubit controllers because we need to send some sequence data, pulse sequence data to qubit controllers. But currently, this circuit does not have a digital processing circuit, unlike cryo-CMOS technology. So, yeah, anyway, there are still many challenges, but we believe that our circuit is very promising because of the very low power operation. Okay, so finally, I will show the other qubit interface circuit, which is flexible circuit. So flexible circuit generates a DC flux bias for calculating the characteristics of each component, such as a qubit and the coupler. And currently, this kind of circuits are used in quantum annealing machines. But I believe that this kind of circuits will be at some point necessary for in the circuit-based quantum processors too for operating the qubit calculation. Okay, so this shows the main part of the flexible circuit, which is a flux DA converter or FIDAC. So the circuit is very simple. So the target device, such as a qubit, is coupled to this flux storage loop, and the magnitude of flux bias can be controlled by the number of flux quanta stored in this loop. Okay, it's very simple. And to apply flux bias to many devices, we need to address many FIDACs in a very scalable way. So, so D-Wave has proposed some very interesting and promising flux bias circuits that use different addressing technologies. And currently, anyway, the point is that it's very important that we can address each device with a very small number of control lines. Okay, and currently in D-Wave's annealing processors, XYZ addressing is used, in which we can apply flux bias to n devices with n-cubed control lines. This is very nice. And also recently, even more scalable flux bias circuit was proposed, in which QFP shift register was used for addressing the FIDACs, and this can reduce the control line count very much. And inspired by these D-Wave's very interesting research, we also developed some scalable flux controller circuits using AQP technology. And this is our flux bias circuit, which we call AQP SFQ flux controller. And the point is that the circuit comprises AQP plus another superconductor technology, SFQ, for addressing and flux storage respectively. And so this is the AQP shift register part, and these are SFQ flux storage parts, and both circuits were bridged by the AQP to SFQ interface circuits, or A2Ss. Okay, so this circuit is very low power because there's no resistors, so there's no static power dissipation, and also because of AQP-based demonstrations, so its power is very small. And also the number of control lines and the supply currents does not increase with the target device count. So because of serial excitation. So serial excitation means that this kind of devices can be coupled to the common excitation lines. So the number of control lines does not increase with the circuit size. And these features are very important to achieve very high scalability. And today I'm not going to into the details of the operation of the circuit, but the operation is like this. We apply digital input signals to this AQP part, and then this data transmit through this AQP shift registers, and then these interface circuits are excited, and the flux quanta are stored into these flux storage loops in parallel. And each flux storage loop applies DC flux bias to a target device via magnetic coupling like this. Okay, and thanks to this parallel programming operation, the programming step count is flux programming step count is relatively small, which is given by n by log m. N is the number of target devices, and m is the flux resolution, which is less than the conventional way in the worst case, given by n by m. So, and as a proof of concept, we also fabricated this circuit and demonstrated at 4 Kelvin. This shows the micrograph. You can see two circuits, but we tested this left one. Okay, and this part is the AQP shift registers, and around here you can see some interface circuits between AQP and SFQ, and this part is the SFQ-based flux storage loop. And in this circuit, a DC squid is coupled to a flux storage loop as a target device. And in this experiment, we measure the magnitude of the DC flux bias generated by this circuit from the DC squid modulation. And it did show the examples of measurement waveforms. In the left case, we stored 6 flux quanta to this device by applying digital sequence of 011, and in the right case we programmed the -350 by applying the digital sequence of 001, And these two signals show the squid modulation. And the thing is that the squid modulation is different between the two cases. This means that the squid modulation is shifted by the DC flux bias generated by this circuit. Okay? And this shows the squid modulation for all 8 digital input patterns. And from these squid modulation shifts, we measure the generated flux bias versus digital input. And this circuit can generate both positive and negative flux biases by inputting some of the control signals. And you can see that for both cases, the generated flux bias can be controlled in a very digital way. So we believe that our circuit can be used to adjust the characteristics of component devices like qubits in future. Okay, so this compares the specifications of some flexible circuits, and I'm not going into the details, but the thing is that by using QFP or AQP shift registers, the number of control lines can be reduced very much. And also, thanks to AQP, our circuit can operate with very small energy dissipation. And today I didn't have time to explain, but it also has some very important circuit features for qubit applications. Okay. So let me conclude my talk. So I introduced one of the very energy efficient superconductor logic families, which is AQP. AQP can operate with very small energy dissipation because of adiabatic switching, which is a very energy efficient logic state switching scheme. And we have, so far we have developed various digital systems using AQP, such as microprocessor, reversible computer, neuromorphic hardware, and a single photon imager. And now we are trying to make very good qubit interface circuits using our very energy efficient AQP technology. So today we show the 2 types of qubit interface circuits. One is the microwave pulse generator. So this circuit can generate multi-tone microwave signals for qubit control in a very scalable way. And the other is the flux bias circuit. This circuit can generate flux bias circuit for flux bias for qubit calculation in a very scalable way. Okay. This research was supported by several research grants. Plus, I'd like to thank all the collaborators. Thank you very much.
Okay, thank you. We have time for some questions. There's a roving microphone with yes, so perhaps let's hand the first question to our host for today.
Yeah, thank you very much. So I wanted to ask again, maybe you already said it, about the logarithm of 2 boundary, how you can actually go below it, because I thought intuitively this must be like a fundamental limit.
You mean this limit?
Yes.
Okay, so the point is that, so this switching process itself is very reversible. So by using this switching process, the circuit can switch its logic state with a very small energy dissipation, much less than this energy limit, because switching process itself is totally reversible. Yeah, but I don't mean that we can perform any calculation in a reversible way. Because, for example, if we make some AND gates or OR gates using our circuits, in this case there's some energy limitation because AND and OR gates are logically irreversible. And this generates also the physical irreversibility. Yeah.
I also thought for switching there is this argument that if you, I think it's called Szilard's argument, right? That if you're able to go from one side to the other, you still have to measure on which side you're originally, and then again comes in this logarithm of 2.
Measure. I'm not sure how the measurement makes difference on circuit at the physical limit, but at least inside a circuit, until finishing the calculation, we don't need to measure each circuit state. So I don't think measurement limits some physical limitation for energy. Thank you.
Question here.
Thank you. Thank you for the interesting talk. It's Martin Takeuchi from INQA. The picowatt figures that you have shown, do they include refrigeration costs? They do.
Refrigerant cost for this energy?
Well, so there are two things, right? Your Landauer bound, of course, is temperature dependent, right? And you're comparing it to CMOS devices, and typically supercomputers do not operate at millikelvin.
So for this comparison, the energy cost for cooling is not included. Yeah. So
do you have an order of magnitude of how that would compare?
Sorry?
Do you have an order of magnitude of how much it would add to
okay, so the energy cost for the cooling will increase this energy dissipation for all superconducting circuits by approximately 1,000 times. So the thing is that the superconducting circuits should operate with energy dissipation smaller than CMOS by 1,000 times. This is very important. Yeah, because we need to. Yeah.
So that puts you quite close to the top of the graph, doesn't it? Or you still pick up an order of magnitude, right?
But so in our circuit, even by adding the cooling power cost, it's still less than the CMOS circuit technology. So it's very important. Yeah.
Okay. That's cool. And my follow-up question is about the multiplexing. So quite often you don't control the exact frequencies of your qubits, especially if you like to control them a lot. And you have given a figure of 4,000 qubits per multiplexer, if I understood that correctly, right? Yeah. Is that an upper bound, some kind of an average, or did you account for the fact that those frequencies, you will have to play around with those depending on what comes out on the qubit frequency distribution and things?
So first of all, yes, these resonance frequencies need to match the qubit frequencies. So this is one challenge. And unfortunately, I don't think we can introduce frequency tunable resonators because we need to apply somewhat large current inside a resonator. So I believe that we need frequency tunable qubits. So this is, I think, one physical challenge or some restriction. Okay. And
so it's a little bit of a no free lunch situation, but
yeah.
But do you again have an order of magnitude of give or take? What would this figure of number of qubits per multiplexer look like once you?
You mean the number of multiplexing?
Yeah. So that the number of 4,000. It's a very impressive, or 2,000. It's very very impressive.
Which is
when you add this one additional level of reality, will this become 1,000 or 100, give or take? Did you have some back of an envelope calculation on that?
Okay, so assuming use of resonators with 10,000 quality factors, 2,000 microtons can be multiplexed per 1 gigahertz. So we assume our 2 gigahertz bandwidth, maybe 4,000 multiplexing is the maximum, I think. So anyway, it's limited by the quality factor of superconductor resonators. So I think it's very important to be able to make very good resonators. I think.
Yeah, thank you.
Thank you.
Maybe one more question about that, thanks.
Thank you, nice talk. I also ask this how to mixing the inside, because this needs local frequency. I understand that we can multiplex, but to do mixing control, so need many parts per qubit, so for qubits. So how to introduce this kind of line?
IQ mixing. So in this circuit, so currently this does not perform IQ mixing. It's just a mixer.
Yes.
And then now we are trying to make IQ mixers by by doubling each AQP mixer circuit. It's possible. Yeah, but in this design we don't have IQ mixers. Okay.
So you mentioned we can achieve the IQ mixer in the cryogenic?
The IQ mixer is possible, yes.
Also, I mean, how to generate the IQ parts, was it inside or not?
Okay, but we need to apply this kind of multitone microwaves from outside, and also plus we need to apply the baseband or IF signals from outside, yeah.
Yes. So how to separate this IQ line per for the qubit, each qubit?
Separate.
Because IQ pulse, each qubit is usually different pulse shape.
Pulse shape.
Yes. How to separate the pulse shape?
It's a good question, and currently the micro pulse shapes are the same in this circuit for all output ports. Yeah.
Okay, I understand. Okay.
So
can I have one more question? So what's the size of this chip?
Chip. It's a very good question. So currently you can see that the mixer is not so small. The size is limited by some bandpass filter design here.
Yes.
Yeah, and unfortunately I'm not so familiar with the arithmetic design, so maybe we can miniaturize the size. But currently, size is something like this. Okay. Not very small.
Not okay. So okay. I understand. Thank you.
Thank you.
Maybe I can use Chairman's privilege to ask a question. So if I've understood correctly, your AQFP device looks a lot like a flux qubit being annealed.
Mm-hmm.
So have you thought about maybe doing some annealing experiments with your AQFP in the thermal regime? And again, you're talking about doing some measurements at 10 millikelvin. Do you think that tunneling will be an issue?
You mean AQFP, annealing using AQFP?
Yes.
Actually, AQFP is almost the same as flux qubit, so
yes.
It's the same to the D-Wave's flux qubit-based annealing. Yeah. And currently we tested this circuit only at 4 Kelvin. So I'd like to see what happens in 10 millikelvin too. Yeah.
Do you think tunneling could be a problem for you, for your control electronics?
I'm not sure. I have no idea.
Well, good luck with that experiment.
Yeah. Thank you.
Okay, so let's thank Dr. Takeuchi again for a very nice presentation.